This may be one of today's most debated concrete products. Inside a rebar bed over 100 meters long, workers place an unusual core, a huge foam block filling nearly half the space. Then concrete is poured over the foam. Some call it smart, lightweight construction. Others question how long it will last. This is a foam core precast concrete panel. It is used in many modern buildings. The idea is simple: cast it in a steel mold. Then send it to the site ready to install. Before production, workers build the outer form with steel plates. After the corner bolts are tightened, they bring in spray guns and coat the mold with release agent. It separates steel from concrete. It keeps hardened concrete from sticking. Without it, removal is harder. Next, a rebar cage is lowered in. It spreads load through the slab. It is built to exact size, so it fits inside the mold. As the cart moves the mold forward, workers in hard hats guide the cage by hand. This is the first main steel layer. It is made from strands and bars. Compared with normal ribbed rebar, steel strands handle higher tension. That is why they are used here. They help the panel carry more weight. Side shear bars are added next. These bars are about 3 centimeters thick. Workers adjust positioning tools to release the panel later and keep the steel aligned. It looks simple, but position matters. Next, the steel strands are tensioned. In simple terms, here's what is happening. The strands are pulled tight. Only then is concrete poured around them. When the concrete hardens, the tension stays locked inside. That tension strengthens the slab. This is press-dressed concrete. After curing, the strands are released, and the force moves into the panel. It works like a bridge beam. The beam must carry heavy loads, so during production, the strand force is carefully controlled. The strands are fixed only where needed. This helps form the bearing surface at the bottom of the mold. A foam spacer is placed. It raises the inner height, helping the strands stay on a steady plane. Now fresh concrete is poured. The mix was prepared earlier to reduce dead weight. The plant uses an overhead track as each section is placed. The cart lowers, but this part matters. The first layer stays thin. It is only about 4 centimeters, and sometimes even thinner. So what fills the space above? A foam board at least 15 centimeters thick. This foam board makes the panel lighter. Foam fills nearly half the panel volume. Metal hooks tie the sections inside. Whatever shape enters the mold becomes the panel's final shape. So the real question is, how much weight can it carry? Above the foam, workers add another steel frame. It uses smaller rebar. The bar diameter is clearly thinner. It helps with positioning and support. Where the middle section sticks out, workers cut it open with pliers. This makes room for angle bars without moving the cage. For now, these bars are not structural. They mainly control shape and alignment. Each cross-section is spaced about 20 centimeters. They are installed in pairs. From end to end, over 20 sets are used. Then workers tie them with wire. Once the frame is tightened, the next pour can begin. The pouring machine follows the track. Its hopper is filled with concrete. Each short move forward releases a measured amount. This pour uses less than expected. Some areas stay partly exposed. That may be for the next step. After each section is poured, workers bring out concrete vibrators. They vibrate the surface, moving from end to end. This removes air, too many air pockets. Can weaken concrete and cause cracks, but vibration has limits. Near the foam, gaps can remain. Those spots are harder to clear. Once the surface grooves are formed, the panel enters the curing area. It is prepared for steam curing. This step takes time. Sometimes 9 panels fill one cycle. Steam escapes near the wall corner. Once the steel door is sealed, heat and pressure build inside. After about 4 hours, it looks like this. The concrete is now very hard. The tension steel strands can be released from the ends. The leftover ends are no longer useful. They are sold as scrap. At the same time, the side molds are lifted away. So why mention trapped air earlier? Because no process is perfect. Next, lifting hooks. Attach near the front and rear corners. With a controlled pull, the panel rises from the mold. Steel ends on both sides are cut before the panel leaves. This is one foam core precast slab made with layered pouring. But this workshop also makes another type. This second type is more complex. It is called complex because this is the cast is 100 years long. An entire factory bay is used for one continuous slab. Here, stronger coiled strands are used, so heavy pulling equipment is needed to tension them to keep the pour accurate. About every 10 meters, workers install a positioning frame. Beside each frame is a round 4-hole plate. The holes match the slab openings. They can carry wastewater drainage or electrical and utility lines. Hydraulics keep pulling the strands. This time, the strands are longer, which means more pulling cycles are needed. If there are 10 strands, that can mean over 30 pulls. Another difference is the concrete mix. It is wetter and looser than the earlier mix. That creates a clear contrast. This kind of concrete cannot simply flow by itself. So the factory feeds aggregate into the mold first. Then it compacts the edges as it moves. This forms the slab's outer shell. Most importantly, the center mold forms hollow channels. At this point, the concrete looks flatter and more even. The sides vibrate as moisture leaves. Water and fines come out at the edges. Because the mix reaches tight spaces, the grooves once made by hand are now formed by a mechanical device. The spacing stays more consistent. The black lines in the middle mark future cutting points. Otherwise, even with a 100-meter slab, no truck could carry it whole. Soon, the machine is lifted away. Extra concrete remains at the front. That material is not needed. Workers clean it up before it sets. Each black circular disc matches the hollow openings inside. Every future cut section gets one of these covers. They keep debris out of the channels. So how is a slab this long cured? How is it actually cured? More precisely, it does not need a steam chamber. Instead, workers cover it with a curing sheet and let it harden slowly. The sheet keeps moisture inside. After about 1 day, it fully hardens. Natural curing takes longer, but it is simple and reliable. Many rural cement roads cure this way. They are covered while hardening slowly. Now curing is complete. The long slab must be cut. This machine beside it uses several tons of counterweight. When it presses down, the ground-level cutter rises into position. Now the saw follows the mark cleanly. CNC positioning saves a lot of manual work. When the front cut is nearly done, the rear mechanism hooks both sides and moves it to storage. Hidden areas inside the slab are now visible. Look at the steel inside. This shows the pre-tensioning method. Along the cutting path, residue is scattered around. Workers do not scrape by hand. Machines feed forward and clean most of it. A worker only sweeps the dust or sprays a light mist. So when people ask about foam core slabs, the real question is where they are used and why does the foam still cause debate?